So hello everyone. So thank you again for attending our this week Rutgers Efficient AI seminar talk. And today we have the Dr. Murali Emani to give us this talk for the interplay between the ML and the systems. So Murali is currently assistant computer scientist in the data science group with the Argonne Leadership Computing Facility at the Argonne National Lab. Prior to this, he was a postdoc research staff member at the Lawrence Livermore National Lab. He obtained his PhD from the School of the Informatics, University of Edinburgh. And his research interests are in scalable machine learning, emerging HPC and AI architectures, online adaptation, parallel computing, parallel programming models, high performance computing. And he serves as the chair of the ML-Perf HPC group at MLComs to benchmark large-scale ML on HPC systems. So as we know that ML-Perf is a very important benchmark to evaluate the current machine learning and AI systems. He also co-leads the AI Test Pad at ALCF to evaluate AI accelerators for scientific machine learning applications. So now let's welcome Murali to give this talk.
Thanks for the lovely introduction, Bo. And I'm glad to be here talking about some of the works that we have been doing recently. So it's trying to focus more on a generic sense. So we're trying to understand the complex interactions between the machine learning and systems. And you see, this is a very active area of research. There are a lot of challenging problems, and there's a significant thrust on even coming, coming from the industry, from the academia, even the industrial labs as well. Even the Department of Energy is gearing towards this particular field. So let me get started now. Yeah. So we see that. So I'm from the Argonne Leadership Computing Facility. This is a U.S. Department of Energy lab. So our primary goal is to help run the scientific applications from different disciplines on our existing supercomputers. So on the left-hand side, so we see that some of our sample applications, which are from different domains, like there's a project called Kernel, where we use deep learning for precision medicine to cure cancer. And also there's a lot of recent work from last year on analysis of COVID-19 proteins. And even in different other domains like in physics and astronomy, there's also significant work on how do you identify neutrino particles and identifying the elliptical and spiral galaxies. So even in the other disciplines such as material science, molecular simulations. So you see that there's a lot of scientific applications are running on this massive supercomputer. So on the right-hand side, we see this is the upcoming exascale supercomputer at Argonne, that's Aurora. So we see that the main purpose for all the HPC centers is to how effectively we run this the scientific applications on this these powerful systems. So we so one clear linking between these two is that the machine learning part, the systems, they're kind of interdependent. It depends on what kind of applications that we are running, targeting, what kind of platforms that we are using, and even if the scale, so running from an edge devices, the tiny devices, all the way till the HPC and supercomputing scale systems. So this is a very much relevant issue. So we need to have more understanding of how these two interact with each other. So we also see that in apart from the regular simulations that are a pretty common scenario for the science application, so we also see there's a significant interest of scientific machine learning. So we are incorporating machine learning and deep learning techniques into these scientific simulations. So some of scenarios, some highlights are we are using some kind of a surrogate models where you're kind of either replacing the expensive simulations with some AI models, or you're trying to learn what spaces to sample and how do you steer your simulations based on some AI-driven models. So that's actually catching up at very, very fast pace. And also coming to the data-driven models. So we see that the simulations can actually consume a lot of resources, both in time and also in terms of the available platforms and the kind of expensive even the investment. So without running simulations with the existing data, so can we build some models to help run them? And the other direction is also like, how do we have the co-design of experiments? Like if you're trying to run a new physics experiment or so, how can you blend the simulation planning of the simulations of the runs, and if you can have a co-design of these experiments of the science runs. So what's really important here is like, how do we design the infrastructure for catering to the scientific machine learning applications? So towards this, so let's talk about one direction. So how can we use systems for ML? So we see that there are different areas are quite important for us, but I'd like to highlight two specific works in this area. And by no means is a kind of exhaustive list. So one is if you're trying to use or the leverage systems for running the machine learning code. So it's really important for us to understand and characterize these workloads and how can we benchmark this system, the models for different hardware platforms. So I'll talk a little bit of how do we do a systematic benchmarking on diverse systems. And then also I'll continue on. We see there's a tremendous growth in the AI specific accelerators. So they're tuned for the AI workload. So how can we leverage those systems for accelerating the science applications? So for the benchmarking part, so I'll talk about MLPerf HPC. So as Bo mentioned, so I'm co-chairing the MLPerf HPC group. So here what we do is we're trying to come up with some the benchmark suite for large-scale machine learning problems on HPC systems. So we see that there's a new era of supercomputers that's coming in the near future. So we already have Perlmutter system at NERSC at Lawrence Berkeley, and we're also having the Frontier and Aurora systems coming soon. So they're poised to be the exaflop machines, so these are exascale supercomputers. And the similar efforts are prevalent across different geographies, Europe, China, and the other countries. And one characteristic, if you see across these three systems, is these have very distinct hardware features, like they're built on different platforms. So for example, Perlmutter is based on the NVIDIA A100s, Frontier is with AMD GPUs, whereas Aurora at Argonne is building up with Intel GPUs, Intel accelerators. So as I also mentioned earlier, this is across these different DOE labs, there's a lot of work going on in incorporating AI into the HPC, the simulations. And they're kind of unique and distinct from the traditional models that we see in industry. So the domains are different, the problems are different. Other important feature is in terms of the data that these applications run on. They're pretty massive when compared with the traditional industrial data sets. So these are classified as, there's a very interesting workloads that we want to evaluate on the HPC systems. So, and even there has been significant discussions on like what should be the path forward in terms of prioritizing our efforts from the Department of Energy. And there's a AI for Science technical report that has been put forward from different stakeholders, like both all the labs, academia, and the industry. And as we see that the systems are also pretty good at running the ML applications, and HPC codes are also looking integrating them. So how do we understand this better? So one significant step we need to do is we need to have a good set of benchmarks for analyzing this emerging and evolving domain. So one primary reason is so we need this kind of a diverse set of benchmarks to assess what's the HPC system performance and how can we drive innovations in both the systems and also even in the methods. As we know that there are different benchmarks like the top 500 HPLAI and HPCI 500. So they are focusing on specific benchmarks or separate capabilities. So we also want to make sure that we are not just focusing on one specific benchmark, but we need to have a representative workloads that are realistic of what scientific applications run on the systems. We also need to test them that these benchmarks actually push on the systems, and that's how they are trying to expose whatever issues that can occur at scale. And as I also mentioned, we need to have a striking balance between the targeted and a holistic strategy, like we are having between a specific benchmark versus a diverse set of models, and also what is a good standard way to actually do benchmarking. So there's a lot of effort going in that front. So ML Commons is trying to address that particular problem. So ML Commons is a consortium, it's an open engineering consortium. So it aims to accelerate ML innovation through ML of benchmarks, there are public data sets, and also there's a best practices. And ML Commons has different groups in its umbrella, like training, inference, HPC, science research. So what they're trying to do is trying to cater to different kinds of problems and also looking at different scales. They also have the edge and tiny and all the way till HPC. There's also a science group which are focusing on scientific applications. This training and inference are for the traditional models in those domains. And there's each group has its own specific set of benchmarks corresponding to what their primary focus area is. So one common theme across this is like, they're trying to define some benchmark applications with some the baseline or the reference implementations. And each group has their own timeline or a schedule where people can run those benchmark applications. They can submit whatever innovations that they are doing, and there are some specific rules and for each submission that needs to be followed, because we need to have a more systematic way of measuring the performance. And there's a review phase for all the submissions, and finally the results are published. So this is kind of a common theme across different groups. So the submissions are of two divisions, the closed and open division. So closed division is where all the submissions have to be kind of equivalent to the baseline implementation. Now, they can be tuning of certain hyperparameters or some changes to their implementations, but so mathematically it has still to be the same as the baseline model itself. While open division is kind of more flexible in that sense, we are encouraging innovation, like people can change the model architecture and do more innovative solutions, but it has to be within trying to measure what is the quality metric for each of the benchmark suite. And there are certain rules like how do we run the benchmarks, what hyperparameters have to be fixed, what can be changed, how many number of runs the benchmark has to be run, and how do we report during a standard logging method. And as I said, so there's a peer-reviewed process, and also the results are published at after the end of this review phase. So that's the more a common theme across ML Commons. Now I'll talk more about the ML of HPC. So as I said, so we are part of the training in the MLPerf group, and it's kind of chaired by Stephen Farrell from NERSC at Lawrence Berkeley Lab and myself. And we have a wide group of people who are active members of this group, spanning across different centers in US, Europe, Japan. So this very active group we had. So we released the first benchmark suite last year, and we also hold different community building activities like the bird of a feather sessions at supercomputing, And we also gave some talks at top tier system conferences like ASPLOS, HPCA. And we have a paper accepted in the MLHPC workshop in SE, that's next month. So I'll talk more about our initial benchmark. So as I said, so we launched the first benchmark suite in 2020. So this benchmark suite is primarily catered for the scientific ML applications, and the reference implementations are all public. So the first benchmark suite has two applications, the Cosmoflow. So Cosmoflow application is published in Supercomputing 18. The goal of Cosmoflow is we're trying to predict the cosmological parameters from this n-body Cosmos simulation data. So it's a kind of a volumetric data that's being generated from the simulations, and internally the model it's a 3D CNN, and it's doing regression of 4 different parameters. So as I said, the models we are trying to incorporate need to have some target metrics. So what's the convergence criteria? So there's an absolute error MAE value set for that. And the other interesting aspect is in terms of the data set. So I said this is all volumetric data, and the total data size is 5 terabytes, which is massive for the simulations. So the next application is DeepCam. So DeepCam code is the application is trying to understand the weather phenomena. What is the extreme phenomena from the climate simulation, which is a pretty hard problem. And this work has won the Gordon Bell Prize in supercomputing. So underlying the model is a DeepLab V3 plus model. So basically they do a 2D semantic segmentation of the images, and the goal is to identify 3 classes of like on a per pixel basis. So whether if it's a tropical cyclone or atmospheric river, or it's just some background noise. The target metric for DeepCam is the accuracy. So it has to be more than 0.82 to say the model has met the convergence criteria. And the total size for this data set is 8 terabytes. So both these applications, so the papers are available, and also the reference implementations are publicly available. So some important characteristics of these applications are, like, if you're trying to compare with what's different from a traditional industrial code, say, right, Resonate 50 or a unit-based model, right? So as I said, Cosmoflow is built on a volumetric 3D data rather than true data, which is commonly employed. And so DeepCam has more higher resolution images, like it has 768 by 1152 pixels and 16 channels, so which is significantly larger than, like, say, an ImageNet. So these two are, like, a kind of striking features, or like how can we contrast them with the traditional workloads in the industrial models. And the other thing is also in terms of the massive data sets, where we introduce significant IO challenges. So these actually expose the whatever the issues that can come from storage and interconnect and how performant they are. And as with any simulations on HPC systems, there's a lot of IO movement happening. So what the systems they usually do is, so they have this node local storages, which are like high bandwidth, and we have very performant IO performance for that. So all the data staging is also included in the measurements. So the data which is residing in the file system, so it is copied to the node local storages, like for example NVMe for NVIDIA systems, and then the data is fed to the hardware for training the model. So when we're trying to measure the runtime, so we are including the data staging time as well. And the metric for both these applications is the time to convergence. So we start with when the data staging has started, and the model training exits when we meet the target criteria, and we measure the time to solution, the time to convergence, and that's the performance metric for these applications. So we have some rules, like how do we run them. So as I said, so we run like few iterations per benchmark. Like we have 10 runs for Cosmoflow, 5 for DeepCam, because it have some stability in the convergence. And we also compute, after removing the outliers, the fastest and the slowest run, we measure the arithmetic mean. As I also mentioned, we also include the data staging time in these measurements. So for the first round, so we had submissions from 6 organizations and systems. So we from CSCS in Switzerland on the Pistayan, from Fujitsu, Riken on Fugaku. So Fugaku is the top, the fastest supercomputer according to the top 500 list. We also had from Corey GPU at Berkeley, HAL at NCSA, and Frontera at TAC. So we see that if you see this list, so we have a diverse set of HPC systems. So they are diverse in terms of their hardware, in terms of the scale of submissions. And we also had the highest number of the largest runs so far at MLPerf. So like it's roughly for the open division, we had an entry from on 16,000 processors, so which is a massive scale if you're comparing the other MLPerf submissions. We also had an entry where we're using mesh TensorFlow to incorporate, it's a hybrid data and model parallel implementation. That's coming because of some issues when you're trying to scale, you improve a certain batch size, and the model was not meeting the convergence. So they had to innovate, like how do you split or change your model and incorporate the spatial decomposition and model parallelism, along with the data parallelism that's already included. So this is the list of the performance. So these are also publicly available. So here we are showing the plot on the different system. What are the hardware platform, the number of accelerators or the processors, what's the software stack each is using. And the last 2 columns show the benchmark results. So I said, so we are measuring the time to solution in minutes. So at the look of it, it's kind of hard to compare. It's not an orange to orange comparison. Then we see that the numbers actually can depend on what platform that they're running, what's the class of the heterogeneous device, like for example, P100 versus V100, and the number of the accelerators. It also depends on the software stack. If you're using PyTorch or TensorFlow, or like by TensorFlow 2.2 versus TensorFlow 1.15. So there are different ways of entries in this particular submission round. And as I said, so we also have this paper accepted in the MLHPC workshop at SC, where we talk more about the analysis of what's the implications of these hardware and software platforms on the performance metrics. So what's happening currently is, so we're also working on the next round of submissions, version 1.0. So in fact, we finished the submissions maybe last week or week before. And so the goal is to come up with similar results during supercomputing in November, mid-November. So some improvements that we had compared to the previous round were, so there are some issues that we identified in the baseline implementation. So we are trying to address those. Apart from these 2 models, so we had a third application included. That's the Open Catalyst model. So this Open Catalyst application has a bunch of different graph neural network based models, and we had this TimeNet++ model included into that. Even the data set is also massive, as is with Cosmoflow and DeepCam. And going forward, our plan is to incorporate more workloads from this particular domain. Like, can we have some throughput based models, or can we have some coupled application which include both AI plus simulation workflows? So that's our goal that we are taking forward. So right now, last year we had this strong scaling submission. Like we run them the codes on a large scale and just get the time to solution. But in the version 1.0, we are also getting the weak scale submission. Like we run an application at a scale, and we run like multiple instances of those applications, and then we report the throughput for that. So the primary reason is that the traditional scenario, the HPC center, so a lot of applications actually share the systems. So trying to run multiple instances and measuring the throughput is a more realistic way of measuring the system behavior along with the strong scaling. So watch out for more the results and some of the analysis during supercomputing. And also, if anyone is interested to participate in this working group, so we meet every Monday, and please join us if you're interested to getting involved in this effort. So now I'll switch topic to the next area. So I said, like, first we're talking about benchmarking stuff. Now next we're talking about the AI systems, right? So so we see that there's an emergence of AI accelerators. So these include the traditional GPUs, like say the NVIDIA DGX boxes. We have AMD GPUs. We are kind of tuned for accelerating the AI applications, and there's a plethora of the AI systems. They are kind of tuned and they're built from the scratch for performing the AI task much better. Some of the underlying hardware changes could be they have the reconfigurable data flow architectures, and they are like software driven. So they can be tuned based on what model is running on them, so based on the application needs. And they also like the custom hardware, which is kind of tuned to accelerate the core AI operations. For example, how can we run, like say there's a gem kernels, which are matrix multiplications, or if there's some kernels which are bound by the memory or the IO bandwidth. So how do we accelerate them? So can we have more configurable way of customizing the hardware, and how can the software stack map these applications, the AI applications, onto their custom built hardware? So that's what they're trying to get the best of the hardware along with their software stack. And the goal is also, to accelerate the training and the inference phases, and also to run large models, which are not possible with the traditional implementations. So towards that, at Argonne Leadership Computing Facility, so we have this AI pathfinding activity. So we have established an AI test bed. So what we do is we maintain a range of hardware and software environments for a wide range of AI accelerators. So the goal here is to provide a platform where we try to test those systems for different applications. We're trying to benchmark them, work on different programming models and machine learning frameworks. And also our main interest is how do we enable the scientific machine learning applications, which are traditionally running on our systems? Can we use these AI accelerators to boost their performance much further? And we also work in close collaboration with different vendors in working with their product development, be it the software stack or even in their hardware resources. So there's a significant effort on this front. So currently we have 4 AI accelerator systems, and this is apart from the NVIDIA DGX boxes, the A100s that we have at Theta, and we're also getting a Polaris supercomputing soon. But I'm talking mostly on the AI accelerators here, the testbed systems. So we have currently 4 of these. So we have the Cerebrus, Sambanova, GraphCore, and Grok. We're also having an ongoing engagement with other vendors, and will be procuring additional AI systems going forward. Yeah, so we also have this public website, the ai.alcf.anl.gov, where we list out our different systems, what configurations that we have, and what work we are currently doing. So here I'm showing like different a snapshot of few applications, the science applications that are currently running on these systems. Like so one is the cancer drug response prediction, the Candle project, and we have this fast X-ray Bragg-Peak analysis, where you're doing more identifying the peaks of the based on the X-ray images for different domains. The protein folding application, that's a priority application for us. And we're also understanding the gravitational wave experiments and identifying the galaxy formations on the AI system. So we are they have been ported to the different AI systems, and there's also other works progress for different applications. So I would say this is a very active area of interest, And we're also seeing significant improvement, or we are trying to run this codes on the NVIDIA the A100 systems along with the AI accelerators. And here I'm also listing a few publications that we had recently. So one is talking about what applications that we run on the Sambanova systems. And the second application, we're talking about how we are coupling running simulations and the learning part. So I'll highlight on one application, the second one. So the application is called StreamAI-MD. So the project is working like how we are integrating simulations which are running on the Theta supercomputer, and we also coupling the simulations with learning that's happening on an AI accelerator. So it's coupling the simulation plus learning from the system side, and the methods from the hardware side. We are doing a tight coupling between the large-scale supercomputer, the Theta GPU, and the system on the Cerebrus as AI accelerator. So the goal here is we are trying to incorporate some deep learning models to drive the molecular dynamic simulation, and it's happening in a streaming manner. The problem is when you're trying to run this lot of ensemble of MD simulations, so they generate a lot of data. The problem is that the scale of simulations is pretty massive, and if you see, there are certain hardware like Anton, which are tuned, they're kind of built for running these MD simulations, but they're pretty challenged by the size of those systems. So what we want to do is to take an alternative approach of incorporating some AI techniques for that, and can we leverage the existing platforms. So here, this is the workflow that we are using in this project. So in terms of the molecular simulations, we are using analyzing the protein structures. And we also, in the paper, we also talk about two different proteins, NSP10 and NSP16 for the SARS-CoV-2 proteome. So what we're doing, trying to understand is how the proteins interact with each other. And that's, we do a lot of simulations at the molecular level. So we run some MD simulation codes for doing those runs. And from the simulations, we generate something called as an input contact matrix. So these are the contact maps. And then we do some embeddings on the latent space to reduce the dimensions, and also get a more systematic way of identifying what spaces that we want to explore. So there's an inbuilt CVAE model, which is autoencoder. And so one of the primary goals for us is, like when you're trying to sample the space of analyzing the simulations, so even the state space is pretty massive. And what we want to understand is, can we have a more intelligent way of exploring the state space instead of doing this exhaustively. So for that, we include some additional learning methods here, and we track what are the important states that we need to sample, and we have offload that techniques to the AI accelerators. And based on the output, so we pass them as other input to our simulations that are happening. So if there are any interesting observations that we have, so based on there's an outlier detection stage, so we try to steer the simulations accordingly. So for example, if we find that whatever given simulation is not interesting enough based on these RMSD values, so we stop the simulations, and we try to steer the next round of the run with a different subspace. So what's happening internally is we are using the AI models to steer guide the simulations accordingly, so that we have a better result at the end of the workflow. So here I talk about like how are we doing the decoupling. So that's more of the work from the application side. So here we see that we are trying to map the simulations and the training. There's a couple with the GPU cluster. We have the NVIDIA DGX boxes with A100 GPUs, and there's a Cerebrus accelerator, a CS1 system. So the MD simulations, they are run on the Theta GPU, whereas the data from the simulations, they are continuously streamed and they're trained on the CS1 model. The importance of also streaming here is that sometimes the model training could take longer times. And by the time the training is done, whatever stage we are exploring could be obsolete and we are like wasting our resources there. So we also want to accelerate that learning component. So this is a more detailed picture of the workflow here. For example, if you, let me point it. So if you see this different node, the Theta GPU 02 all the way. So we are running this MD simulations through OpenMM application. And each node has 8 GPUs, GPU 0 through 7. So once these simulations are running, so we write frames through the to the SSD, and then we transfer those frames to the Medulla cluster. So Medulla is a cluster which holds the CS1 AI accelerator, the Cerebras system. And from the frames that are read to this cluster, so we pass them to as input to the CS1, where the where model is trained based on this streaming data. So the goal of the model is that the CVAE, where we're trying to understand what are the important spaces to explore. And once the model is trained, we just pass those weights back to the a single node of Theta GPU. So we are doing the outlier detection on a single GPU. So whatever models that we have trained on the CS1 system, so the learned weights are transferred back to Theta GPU 01, that's a dedicated node. And that's where the outlier detection algorithm takes place. So based on that, again, the data is passed through the Lustre file system to the rest of the nodes. And that's where we're kind of, based on the inputs, we are trying to either launch an additional OpenMM simulation with a different state space, or you're trying to stop the simulation if it's not interesting or if it's an outlier. So that's the way that we are kind of coupling these simulations on the supercomputer with the learning happening on the AI accelerator. So this is an observation that we had from this experiment. So here we see we are trying to measure the protein-protein interaction between NSP10 and NSP16 proteins. So if you're doing them on a traditional A100 versus the coupling part, so that's what we are trying to analyze here. So because of the memory limits, so we are restricted on using a certain batch size to 64 on the A100, whereas on the CS1 we can accommodate a larger batches of 512. If we just measure the throughput in terms of the number of samples per second, so we get roughly a 3.7 times improvement in throughput when you're doing that on CS1 versus on a single node on 8 A100 GPUs. So also interesting is that we are trying to scale to 4 nodes. So we get a much higher improvement, though we are kind of sacrificing these nodes for simulations because we are sharing the Theta GPU nodes for running the simulations as well. The few insights and few learnings that we had from this experiment is that we are running this the numbers that we had using single precision on A100 while we're using the mixed precision on CS1. So at the time of this experiment, so we had some issues with running the codes with the mixed precision on A100. That's recently fixed as well. So this experiment shows like how we are able to improve the performance of the codes with given a context of the molecular dynamic simulation with the protein-protein interaction. And we are measuring between the NVIDIA A100 versus coupling them on the CS1 accelerator. Okay. Now let me quickly switch to the other topics. So now these two topics I was talking mostly on how can we use systems for driving the ML applications, like how do you categorize those benchmarks, how can you leverage those coupled systems for the scientific machine learning applications. Let me switch gears to the other way around, like can we use ML for systems? So even this has been a very active research area for a while now. I'll be talking a specific problem that we worked on recently. So we are using the machine learning driven approaches for memory optimization on GPUs. And this is a joint work with my collaborators at Lawrence Livermore National Lab. So we see that with a unified memory, where we have a single view of the memory between the host and accelerator, between the CPU and GPU. So there are primary advantages with unified memory in that it has this explicit copies, and also there's a zero copy access. And it also eliminates the need for a manual or massive data migration across the host and device. It's error prone and also expensive. So if you're doing a quick comparison, like how do we do the explicit memory management versus the one with unified memory? So see the left-hand side. So we see we need to first allocate some memory chunk on the host. Then we have to do some copies to the GPUs using some CUDA APIs. But if we had this unified memory implementation, so we see the data is allocated initialized on the CPU. When you call the kernel, it internally takes place, analyzes like where the memory is residing and how the memory is copied. So that's all taken implicitly. So that eliminates needs of having a better way of managing the data transfers across the host and device. So there's an API to help advise the unified memory driver. That's the CUDA memory advice. So what CUDA memory advice does is, so we are trying to talk of a given data object, and there are different memory advice options that are provided, which can actually impact like how the data is used. So using this API, we actually can specify which choice of memory advice that we can actually implement. And there are, as I said, there are different ways to do. So one is the default way is there's something called the on-demand page migration. So based on a first touch policy, if the restrict is coming from the CPU or the GPU, then the pages are migrated accordingly. There's also a set read mostly. So that's applicable for data which is mostly read-only data. And there's another option for set preferred location, or also like set access by. So there are different ways of specifying what choice that we can give for working with the unified memory. Now, if you're trying to run across with these different options, so what's the impact on the kernel performance, right? So here we are measuring the speed up of different variants with the Gaussian benchmark. So we see that the 7 variants, 1 through 7. Here we are trying to see the what's the range of the kernel latency, the execution time based on the different variants. So we observe that the different choices can have significant impact. Like you can get up to 3.5 times improvement on the speed up. On the other hand, by choosing a wrong choice, that can lead to it's a 200 times degradation in the performance. This is just for analyzing how important is this setting this particular code variant on the kernel execution time. But I said, so it's important for us to identify the ideal memory option, but it's kind of very tedious process, and it's extremely challenging for programmers to decide like how do we use unified memory, like should we use unified memory, or if I want to use that, like what is the better option for a given memory object. So to tackle that problem, so we proposed a machine learning based model to guide the memory advice problem. So we have a 2-phase approach. We use this offline training and online inference phase. So this is the workflow that we have for the offline training. So we had some set of benchmarks, and we are running them with different memory choices. Like for example, we have benchmark I through benchmark K, and we run them using different choices here. And during this offline training process, we also collect some runtime metrics, which are formatted to a data set that forms a training set for our offline build classifier. So the output of the classifier is so given this input set, what's the best memory option that we have from the 7 variants. So I said in the training phase, we collect a lot of metrics, and we use NVIDIA Insight tools for that. from that, we have the tool generates a bunch of different metrics that corresponds to what's the compute memory behavior, also the hardware level information on the DevOps, the threads, the occupancy, everything. Now it's important to understand which of these metrics are really important, like which can characterize how these kernels are running on the GPUs. So we use some filter feature engineering techniques like correlation and information gain metrics to filter out only the relevant features and that are transformed as the training feature vectors. So upon those methods that we use, so we observed, so these are the important features that are kind of influencing the decision. So it is not an exhaustive list. So for example, if you're running them on a different platform or different set of benchmarks, you might end up with a different set of features. So what we did is, so we used these specific features, the selected subset of features, then we built our classifiers. So for the online inference, so whatever classifier that we have built, so for on the runtime, so we use Insight to extract those 9 or 10 features, then that are passed to this model, and the model is built to give the specific advice for that. And we have built a custom library as a wrapper library, that's Exquisite malloc. So that basically gives us like if you're using unified memory or not, and then whatever option choice the model is predicting, it uses that policy accordingly in the benchmark. And the code is run with the predetermined advice, and we're trying to evaluate that particular application. So here we're using what benchmarks we use for training. So this was on Livermore computing from Rodin and the Larsen supercomputer. So we used a bunch of different kernels from each benchmark and varied the different input data sizes for those kernels. And also from those training sets, so we try to run a bunch of different classifiers to see which one were more accurate for this specific task. So we observed that random forests were getting the highest performance from this the data set that we've collected, and we used that classifier for our experiments. So if you see this evaluation here, so we are trying to run our model and comparing that with the baseline model. So baseline model is we are not using any of those memory advice choices. And if you see the x-axis is showing the different kernels along with their the data sizes. And we see that the execution latency is reduced significantly when we're comparing the baseline implementation versus the model predicted implementation. This for breadth first search, and we also doing it for the CFD code on the right side plot. So we observed that we had almost 40% reduction in the kernel execution latency. And also for the CFD, we had an average of 8% reduction. For hotspot and Gaussian, so we also observed significant reduction, like 35 to 60%. So what we try to do is when we built this, the auto-guided way of doing it, the model is able to capture, how the kernel is interacting with the platform, with the GPUs, and based on the features that we are collecting, our model is able to predict, okay, which of those memory advice choices could be really boosting the performance of the particular kernel, and we do that. And right now we are doing it on a kernel level granularity because of the obvious overhead associated if you're doing it at more finer levels. Yeah, so to conclude my talk, so I've given a flavor of a wide range of problems. So with the systems for ML, so we try to understand what do we need, the systematic characterization and benchmarking. And I've given a flavor of the context of more the scientific machine learning applications, because the problems where we're tackling are different. The models have different characteristics, the data sets are massive, and we are running them on large scale supercomputers. So there's a diverse set of platforms. So so it's important to benchmark those applications and trying to understand those performance. And the second topic I've also touched on, like on how can we use these AI accelerators to understand how can we run them or leverage their performance for driving our accelerating our workloads much faster. And one example I've given is we are coupling the simulation plus learning. That's a very very innovative direction, and there's a lot of emphasis going forward in that front. And also, I've just given another example for using ML for systems. So can we use some techniques from machine learning based approaches to tune system level configurations and on a single node experiments. So with that, I conclude my talk, and I'm happy to take any questions.
Thank you, Murali. Oh,
yes.
Yeah. Thank you very much for your excellent talk. So any questions from the audience? If you have any questions, you are free to unmute yourself.
Hello, I have a question. Can you go back to the work, the project you highlighted for the streaming, simulation and training part? I think. Yeah. Yeah, this part. Yeah. So I was wondering, I'm not quite clear. So can you elaborate what's the key contribution here for this work?
Yes. So traditional way of doing this is, like you're running the simulations on the Theta GPU systems, right, on your HPC nodes, and you also do the model training part on say on a GPU itself. So what we're trying to do is we're trying to offload the training, the ML component onto an AI accelerator. So what we're doing is, so from the simulations, what we are learning, all the latent space representations, we are transferring them to the CS1, the one highlighted in the green box here. So that's the AI accelerator. So we are running our AI models on the CS1 system, and whatever output that we're getting, though, based on that, we are performing an outlier detection. And as I said, so the outlier detection is identifying which simulations to continue or which simulations that you need to restart. Based on that, we are steering our simulations back accordingly. So instead of doing them kind of on a single system, we are trying to map the application, like your simulations are running on HPC systems, which are optimized for that. And the ML, the learning part is offloaded to the AI accelerator, the CS1 system. Okay. This is like one of the first kind of work which is actually doing this coupling of simulation and learning on two different platforms. As I said, so there are more details on this paper. This paper published in past conference and maybe a couple of months back.
Okay. A second question is about your second work, using machine learning for decide the memory management. I have a question about baseline. I'm wondering, what's the baseline?
Yeah. So baseline is you're using the we're not using the unified memory. We're using the discrete memory for all the data objects. See here, variant 1 is the baseline.
Okay.
So variant 2 is if you're using unified memory, the default version, and variants 3 to 7 are you're using unified memory plus additional memory advice options.
Okay. So you are for the baseline, for the speed up, you are measuring the running time of a specific kernel or specific task consists of several kernels.
So we do it at both at an application level and also at a kernel level. So the paper has more details on that.
Okay, thank you.
Other questions from the audience? if the audience doesn't have any questions, so actually I have some questions. Yeah.
Sure, please go ahead.
So can you go back to your slides on that you evaluated the different accelerator in the HPC test bed? Yeah, so like the...
You mean the MLPerf part or the...
I think one slide that contains 4 different brands of the emerging AI accelerator. You said that.
Oh, yes.
Yeah. So here I was curious about that. So so first we know that right now there are many different AI hardware startups. Yeah, like those this is the startup there, and so so from your perspective, so right now, so especially when compared with the GPU, because you another slide that contains that you use both like CS1 and GPU together. So, but actually, so at least like in their product description, they said that like the CS can be also used for training and so on. So from the perspective of the user and the end user, so how do you think about that? And for your target scientific applications, so what about the advantages and the disadvantage of the GPUs and like those are the emerging specialized AI training or inference accelerators for your target applications, and whether we need to utilize such the heterogeneous use of them? So if so, so why one with such heterogeneous?
That's a very, very interesting question. So that's the primary reason that we have the AI test bed at ALCF. We are exploring the systems. So I would say that each of these AI system has their own unique abilities in terms of their hardware. Like each has their own the compute resources, their on-chip memory, off-chip memory, what's the DRAM bandwidth, how are they networked together, and in terms of how they are packaged, and in terms of the software stack. Some systems are kind of, they have their own implementations of running a deep learning framework. Like SambaNova has their stack called as Flow that's built over PyTorch. Like Cerebrus can run TensorFlow based models. Likewise with GraphCore and Grok. And each of their software stack is kind of optimized to run this or map these applications onto their own hardware, right? So, and similarly, when you're looking at the NVIDIA A100, so even that's an, I say, AI accelerator, it's primarily tuned for AI applications too. So what it means is that we need to do an evaluation of based on if my model is, say, it has more of convolution layers, or if it's it has more bandwidth limited operations, or in terms of my the data sets that each model is used. So there are a bunch of different parameters that we need to consider when we're trying to consider if we were to run on, say, a GPU versus one of these systems. And there's no straightforward answer, and there's no direct answer for that. And like you can have, because we have some applications which run on all the 4 systems along with the A100s. So it depends on a different, as a separate the application characteristics and what's the primary goal for us for that application. And also we say like what's the availability of the software stack and the support. Like for example, Grok is primarily aimed for it's kind of an inference engine. So if you were to have only inference tasks, then you can also consider Grok. So so it depends on each of their platform specific options.
Okay. So you think that like the relationship between the GPU and for this the specialized AI hardware is kind of more complementary and not the competitive?
Yeah, you can say in that sense. Like so one distinguishing feature is some of the software stacks you need to if you take a model, right, you have to refactor according to their APIs, but just to get the best performance. So you can say you can have this complementary version of integrating the GPUs with the AI accelerators.
Okay. Okay. Thank you. And another question, I'm a little bit curious about that. Since we already have such the specialized AI hardware, and so whether it's still kind of any opportunities like for the FPGA be used in such kind of AI test bed?
Yes. So right now, so yeah, FPGAs can also be used for like specific tasks, like or maybe you're doing more inference or on edge devices. So right now we are focusing mostly on the systems like these that what we have. We are also getting newer systems, but FPGAs can also be used for a given task. So right now we don't have them in the AI test bed, but that's an open question.
Okay. Okay. Thank you very much. So any other questions from the audience? Okay, so if no more questions, so let's thank Murali again. So this very informative and a wonderful talk. And thank you. And also thank all our audience to attend our talk, and see you next week. Thank you.
Thank you very much. Thanks, Paul. Thanks. Bye-bye.
Have a great day. Bye.